Welcome everyone. Today we're going to start on a new topic, one of our more advanced integration techniques, trigonometric substitutions. So in this lesson, we're going to see how to use a trigonometric substitution to convert an integral involving a square root function into a trig integral. So powers of trig functions, powers of sine, cosine, powers of secant, tangent, things like this. And the benefit of doing this is trig or square root functions are notoriously difficult to integrate, but we have some strategies that we've looked at so far on how to integrate powers of trig functions. So that's the main benefit of this technique, is it takes a square root function and with a little bit of arithmetic and algebra, we convert it into a trig integral. So let's kind of see how this is going to work. And there's primarily going to be three trig substitutions that we do. And they all come down to the square root term that's in our integral. So let's read through this table here and kind of see how things are going to be set up. So we're going to be primarily looking at these three cases of square root functions. So we have the square root of some constant minus x squared. We have the square root of some constant plus x squared. Or we have the square root of x squared minus some number. And based on these three possible cases, we're going to identify what we should pick for x. So this is going to be our actual trig substitution. So we're going to make a choice for x based on whichever square root function we see. Once we choose x, we're going to calculate dx, so calculate our differential. And this should start kind of feeling pretty similar to things we've done so far. Now, the really important point here is this differential. We do need to calculate this. And once we get our choice for x made, once we've calculated our dx, we want to do some work on simplifying that square root term. And this is where you can see why this technique is going to be helpful. So let's look at maybe one of these and see what happens. Maybe we'll look at two, who knows. And where the magic happens, or where the magic comes from, is with our trig identities. So let's just start by recalling two of our main trig identities that we've seen so far. So one of them involves sine and cosine. The other one involves tangent and secant. So what was our sine and cosine one? Well, it was cosine squared theta plus sine squared theta plus cosine squared theta is equal to 1. Sine squared plus cosine squared is equal to 1. And then we also had one for tangent and secant, which said secant squared theta is equal to 1 plus tangent squared theta. So we had these two nice trig identities that we've used before in some capacity with our trig integrals. And they allow us to simplify things down. But where the magic happens is we're going to be able to use these trig identities to really simplify that square root term. So let's look at what happens when we let x equal a times sine theta. We're going to see how that choice for x really simplifies this square root term down. So let's try it out. Let's say we take our square root term, a squared minus x squared, and let's fill in what we're choosing for x. So I'm going to take this a times sine theta, and I'm going to put it in for x here. And that'll give me a squared times sine squared theta. So basically we're squaring x and we're squaring everything here. Well, we see we can factor here. We can factor off an a squared. So that leaves me with 1 minus sine squared theta. And then 1 minus sine squared theta, we know what that is in terms of cosine. So that's actually equal to cosine squared. And depending on the angle here and the value of cosine, and it's kind of a finer point there, but depending on the value of theta, the square root and the squareds end up canceling. So we end up with just a times cosine theta. And so it takes this, essentially what we're seeing here is because of these trig identities, we're able to take a square root term, plug in our trig substitution, do a little bit of factoring, a little bit of simplifying, and then poof, the square root term is gone. And now we just have a nice trig function that we can integrate, or that's part of our integral. So this is where this is the magic for this technique. Let's try one more, just to go through these trig identities. It's good practice. So let's maybe take this last one, x squared minus a squared. Let's see what happens there. So we're going to start with our square root term that's showing up in our integral. Now for this case it says let's let x equal a times secant theta. And let's plug that in. So we're going to get a squared times secant squared theta minus a squared. We can factor off the a squared just like we did. And that leaves us with a squared times secant squared minus 1, all under the square root. But now based on this trig identity, we know what secant squared minus 1 is. That's just tangent squared. And oh boy, the squareds are going away. We have squared, two square terms under the square root, multiplication in between, so we can just square each of those, or do the square root of each of these individually, and we get a times tangent theta. Now there is some subtlety here in terms of we need theta to be, certain values. But we can do this simplifying. So this ends up being a times tangent theta. And so we go from this complicated square root expression, which is going to probably be difficult to integrate on its own, and then we end up with this trig function. And we have a whole slew of techniques for how to integrate powers of trig functions. So this is why the technique is really going to be helpful, because it's going to allow us to kind of sidestep the whole square root issue and instead look at trig functions. We're going to come back to this table, but let's just kind of talk a little bit about the process here. So step one, we're presented with an integral. The first thing we want to do is just decide what the necessary trig substitution for x is going to be, and that's just by identifying those three possible square root cases. So again, what were those cases? There's three cases. We might see square root x squared minus a squared. We might see an a squared minus x squared, or we might see an x squared plus a squared. So we're just looking to see which of those things is showing up in our integral. And based on what we see, that's what we choose for x. So if we see this first one, well, that's going to be, we're going to let x equal a times secant theta. If we see this one, we're going to let x equal a times sine theta. And then that last one, we're letting x equal a times tangent theta. And that was in the chart there on that we just looked at. So if we saw one of those square root functions in our expression, well then we just need to know which trig substitution goes with that square root term. All right, so that's the first step. just kind of look at your integral, decide what you're going to pick for x. The second step is just to calculate all of the other pieces. So differentiate your choice for x to get the differential dx, and figure out what your square root, your simplified square root term is going to become. And if we go back to our table here, we know how it's going to simplify in each case. So you could run through these trig identities for every time you do a problem, or you could just kind of know what's going to happen. So if this is our square root term, and if this is what we're picking for x, then you're always going to end up with this square root term simplifying to a times cosine theta. Same thing for the last one we did. If this was the square root function that you're seeing, this is what you're picking for x, all of this work in the middle here is always going to feel the same. And so you kind of know ahead of time what that square root term is going to simplify to. It's going to simplify to a times tangent theta. So, you can either work through all of this by yourself, or you can just know what the end result is and just kind of state it. So it's up to you which way you want to do that. And a kind of a nice way to kind of remember how that simplifies is I tend to think of sine and cosine as opposites. So when we choose x equal to a times sine theta, well, then the square root term is just going to simplify to its opposite, a times cosine theta. Same thing if we're choosing x equal to a times tangent theta. Well, what's that square root going to become? A times secant theta. I sort of think of secant and tangent as opposites. And then if x is going to be a times secant theta, well, when we go through our simplification of that square root term, it just ends up being the opposite, a times tangent theta. So, like I said, you can go through all this work each time doing the trig identities, or you can just kind of know ahead of time what the result is going to be. So the choice for x and the square root term are sort of like they end up being just the opposite trig function. All right, so that's step 2, is just figure out the remaining pieces for your substitution, dx and what the square root term becomes. And then once you have x, once you have dx, and once you have the square root function, step 3 is just to take all those pieces and put them into your integral. And that's going to give you a trig integral to do. And that's step 4, is go through and calculate the resulting trig integral. And then finally, once we have our antiderivative of our trig integral, it'll still be in terms of theta. So the last step is that we have to convert our antiderivative back to the original variable x. And we'll talk a little bit more about that in a few seconds. All right, so one little quick thing to note here is when we look at these square root functions inside our integral, we're picking a trig expression for x, and we have kind of this, right now we're kind of talking in generalities. So we have this a squared, and then we're using an a here. But in practice, how do we figure out what a is? So let's say we had the expression x squared minus 9, square root of x squared minus 9. How do we figure out what the a value is there? Well, we identify the constant term, and we just look at the positive part of the constant. So you might think of this as like minus 9, but really we're just interested in just that constant piece here, just the positive part. And the value for a then is just the square root of just that constant. So if we see a 9 here, it'd be a equal to square root 9 or 3. So if this was our square root expression, what we would end up choosing for x is, what is it? It's this case right here, x squared minus something squared. So we'd let x equal 3 times secant theta. And so that's how we would pick the constant that goes in front of our trig function. It's the square root of whatever that constant is. All right. So we know how to pick x, we know how to calculate dx, we know how our square root expression is going to simplify, and we'll try these out in some examples. The next major kind of task here in going through these problems is to convert our antiderivative back to the original variable. And to do this, we're going to be using, in a lot of cases, we're going to be using a right triangle. So here's a right triangle. You can see the right angle. Here's theta. So when we're converting into our integrals into thetas, here's theta represented in this right triangle. And we're going to talk about the sides of the triangle. So the opposite side is the side of our triangle that's opposite angle theta. The adjacent side is the side of our triangle next to angle theta. And the hypotenuse is the side of our triangle that's opposite the right angle. All right, so why are we interested in a right triangle? Well, our trig functions all can be related to the sides of a right triangle. So for instance, sine of theta is equal to the opposite side over the hypotenuse. Cosine of theta is equal to the adjacent side over the hypotenuse. And tangent theta is the opposite side over the adjacent side. So we can relate the sides of our triangle to sine, cosine, and tangent. Well, we also have three other trig functions that we work with. We have cosecant theta. And we can also remember, what cosecant is in terms of the opposite and hypotenuse and adjacent sides. But you probably might be helpful to remember them, what they are, just in terms of sine. So cosecant is 1 over, it's the reciprocal of sine. It's 1 over sine. Secant is the reciprocal, it's 1 over cosine theta. And cotangent theta is 1 over tangent theta. So if you can remember sine, cosine, and tangent in terms of the sides of the triangle, and you can remember cosecant, secant, and cotangent in terms of sine, cosine, and tangent, well then you can figure out what the formula is for cosecant, say, or for secant in terms of the adjacent and hypotenuse. So for instance, secant would just be the reciprocal of cosine. So take your fraction for cosine and flip it. So it'd be hypotenuse over the adjacent side. So, however you want to remember it, perfectly fine. The way I remember it is like this. So I have sine, cosine, and tangent memorized for sides of a triangle, and then I remember what cosecant, secant, and cotangent are in terms of those trig functions. And then I can kind of work it out each time. All right, so let's try an example to see how this process works. So this is, like we said, this is one of our advanced integration techniques. So there's going to be a lot of steps and a lot of kind of moving pieces of our integral. So we'll take the first one slow, and it's going to take a little bit of practice here. So let's try out the first one. Let's look at the integral of 1 over the square root of x squared minus 9. So this is a square root function that we're trying to integrate. We can't use substitution rule, just regular use substitution, because once we started trying to convert the differential, we would run into trouble. Not everything would be able to convert. We don't have enough kind of x terms here in order to convert everything. So we're going to try a trig substitution for this one. And let's start it out. So step one, we look at our function and we see it's a square root x squared minus a squared form. So that means we're going to choose x equal to a times secant theta. And how do we pick a? Let me get rid of that minus. It's not a minus there. How do we pick a? Well, remember, a is just the square root of just that constant that we see under the square root. So it's square root 9, which is 3. So that means we're going to pick x equal to 3 times secant theta. All right, so that's step 1. Just choose x. Identify what the square root term is, choose x. Now, the second part is to calculate dx and see how this square root term is going to simplify. So let's differentiate secant theta, and we know that derivative. It's secant theta times tangent theta, and then we put a d theta on at the end. So that's our differential dx. And then how is this square root term going to simplify? Well, we kind of went through the general case back when we were looking at the chart, but we know the end result each time, essentially. So basically, the square root term simplifies, once we go through our trig identity, to just the kind of the opposite trig function. So if we're thinking of secant, the opposite trig function is, in relation to that trig identity, is sort of like tangent. So this is just going to simplify to 3 times tangent theta. So let's just go back to our table just to check that. So we picked x equal to 3 times secant theta, and we're saying the square root function is going to simplify to 3 times tangent theta. So let's look. So we have our 3 cases on our table here. We're in this case here, x squared minus a squared. And we said a was equal to 3. So we said x is equal to 3 times secant theta. So that matches up. We calculated our differential, so just the derivative. So 3 times secant theta, tan theta, d theta. And then we simplified our square root function, and we said it was equal to 3 times tangent theta. And that's what this table is showing. All right, so we chose x, we calculated dx, we saw what the simplified version of our square root becomes. And again, you can just know this, have this memorized, or you can show it all out if you want. And so we have 3 pieces here. So now we go up to our integral, and we're going to plug all of those pieces in. So wherever I see a dx, I'm going to plug in what I calculated for dx. Wherever I see that square root, I'm going to plug in what I calculated for that square root. And if I had any extra x terms, well, I'd plug this in, the 3 secant theta, in for any x terms. So let's kind of go through here. We know the dx here at the end is going to become 3 times secant theta times tan theta d theta. We know the square root term that we have here, we know what's going to happen to that. That's going to become 3 times tangent theta. And that's it for now. That takes care of everything. So let's make the substitution. So let's put all of our pieces into this integral. So the 1 on top is going to stay a 1. That square root term in the denominator is going to just become 3 times tangent theta. The dx here, well, what's that becoming? Well, becoming 3 times secant theta times tan theta d theta. And there we go. We've taken all of our pieces, and now we have a nice trig integral. So there's some powers of tangent, there's some powers of secant, and we're going to be able to work with this. All right, so that's the hard part. Well, I shouldn't say it's the hard part. these are tricky. This is an advanced integration technique. So, you know, there's going to be a lot of little parts in these problems where it gets a little tricky. So, you know, don't feel bad if you get stumped by one of these problems, if something's given you an issue, because this is difficult. There's a lot of things kind of coming together here. And it just takes some practice. But we're at this point now where we have a trig integral. So now we want to simplify as much as you can. And this is kind of the fun part, because a lot of times when you put all these pieces together, you get a lot of canceling. So let's look at this. The 3's are going to cancel. What else? Well, we have a tangent down here and we have a tangent up here. So those are going to cancel. And, you know, once all the dust settles, this comes down to just knowing the integral of secant theta d theta. Everything else just got canceled off. And this one is one we know, or we know that we should look up. It's the natural log of the absolute value of secant theta plus tangent theta. So there's our antiderivative. And we're almost there. We have our antiderivative. Now we just need to convert back to x. And that's what we're going to see next. How do we actually convert this back to x? So we're going to need a little bit more room for that. So let's go over here. Let's write down our results so far. We have this integral is equal to the natural log of the absolute value of secant theta plus tangent theta plus c. And what else? We said that, what was our substitution? We said x was equal to 3 times secant theta. And we also had that the square root term was equal to 3 times tangent theta. All right, so let's draw in our right triangle. And we're going to figure out all of the sides for that right triangle. All right, so there's our right triangle. Oof, can do better than that. Apparently not much better than that, though. All right, so there's our right triangle. There's theta. And we need to figure out what the sides of our triangle are. So we have these parts that we used in our substitution that can help us. So we know we picked x equal to 3 secant theta. And we also know that we picked x squared minus 9 is equal to 3 times tangent theta. So we can use either of these to help us figure out the sides of our triangle. And, you know, let's use this square root one here. So let's solve for tangent theta. So that gives us square root x squared minus 9 over 3. And we know tangent is the opposite over the adjacent side. So this is really telling us, if we kind of just match up the pieces of this fraction with the pieces of this fraction, it's really just telling us the opposite side is the square root term, and the adjacent side is 3. And so what's the missing side? Well, the missing side, you know, maybe we figure that out from our secant term. So we solve for secant theta. Secant theta is x over 3. And we know secant is 1 over cosine. So what's the reciprocal of cosine? Well, it's hypotenuse over adjacent. So this is telling us if we just match up the pieces of our fractions here, it's telling us the adjacent side is 3, which we already knew, and it's telling us the hypotenuse is x. So you can kind of just use those to figure out what all three sides of the triangle are going to be. All right, so let's now look at our integral here. And we just have to figure out, well, normally what we would do is we would have to go to our right triangle, and normally there would be pieces of there would be other trig terms here that we would have to figure out. And that's what we would use our right triangle for. But actually, just from our substitutions, we have enough information now. We know what secant theta is in terms of x, and we know what tangent is in terms of x. So we just plug all that in. So x over 3 is our secant, and tangent is x squared minus 9 square root over 3. And there we go. We have our antiderivative. It's all back in terms of x. We're done. So we're going to see how to use this right triangle in more examples. But just for the fun of it, let's say we went through all of this integration and our antiderivative had a sign in it. So let's just say for fun, how would we convert? What would sine of theta be? Well, we would look at our triangle, and we know sine is opposite over hypotenuse. So if we went through all of our integration and we had a trig function here that wasn't kind of one of our pieces, that sometimes happens, we can figure out what it is by filling in all of the sides of our triangle like we did, knowing what that trig function is in terms of opposite adjacent hypotenuse, and then just using the triangle. So if for some reason we went through this integration and we had a sine theta, well, sine theta is opposite over hypotenuse. We know the opposite side is square root x squared minus 9, and we know the hypotenuse is x. So if we, say, had a sine term in our antiderivative, this is what we would plug in to convert that over. Now, we kind of got a little lucky here. We had all of everything we needed. So we could solve this x equation for secant theta, and we could solve this equation for tangent theta, and that was enough that gave us all the pieces we needed. But if there was other things, well, that's where we would really need to fill in our triangle and then kind of solve for those. All right, so we're going to kind of break there for today. There's a lot to take in with this. So one example, kind of really get a little practice, go over this example, try it again, and that's what we're going to be doing for the next couple days, is just more problems, more practice examples like this. So we'll kind of go through, the procedure, see some more complicated examples, things like where the trig integral is a little bit more difficult, things where like the conversion, there's a little bit more we need to do there. So we'll get some good practice over the next couple days. But this should be more than enough to get started. So have a good rest of your day, and we'll see everyone tomorrow for more trig substitution. Bye-bye.